Okay, welcome to this video where we're going to be having a look at a practice paper for the higher tier Paper 2 Maths exam. Don't forget, you can download this paper from the description, and if you have it printed, you can scan the QR code on the front at any time to get yourself back to this video. So, we're going to get started with question 1. So here we have some standard form conversions. So for this first one, we want to get this number between 1 and 10, which means hop in the decimal 1, 2, 3, 4, 5, 6, 7 jumps. That would make it 3.246. Standard form is always times 10. We just need to decide on that power. It was 7 jumps. It is a large number, bigger than 1, so it is a power of positive 7. If it was a 0 point number, that's when we'd start to introduce that negative power. But here we are, we had a large number there, 7 jumps. So our final answer is 3.246 times 10 to the power of 7. For our next question, we do have a smaller number, which is a 0 point number. Now, when I do this, I rewrite these numbers, so 4, 9, and 6, and I just imagine where that decimal is. If I draw it just above there. For a negative power, we are hopping that to the left. Of course, if we jump to the right, it would be 4,960, and then it wouldn't be a 0 point number. So 1, 2, 3 jumps, that's where the decimal is going to go. Underneath these loops, I need to fill in my zeros and then tidy it up with a 0 at the start. And there we go, I'm going to rewrite that number nice and neat on my answer line, 0.00496, and just make sure that decimal point's really nice and visible there. Okay, so there's some standard form conversions. Our next question is looking at highest common factor and lowest common multiple using this product of prime factor method. So here, when we have a product of prime factors, and you can use this method even if you're given whole numbers instead of these prime factor versions. Now the way that I approach it is I write out the numbers in full in regards to all their prime factors. So here we have 2 2s, we have 4 3s, 1, 2, 3, and 4, and then this 7 at the end. I'm going to do the same with the other number. So 2 3s and 2 7s. And now I'm just going to see what's in both. So I like to highlight them, but you can underline them or do whatever you like. So there is no 2s in both, but there is a 3 here, which is in both. There is another 3, which is in both. And there is a 7 that's in both. Now, all we need to do is multiply whatever numbers are in both. So just using one of them, just looking at either the left or the right here, there is a 3, and a 7. So for the highest common factor, I just do 3 times 7. And of course, you can use a calculator. So I'm going to use a calculator throughout this, and that is 63. And there is my highest common factor. So a really nice quick way of getting the highest common factor there rather than writing down all the factor pairs. And of course these are quite large numbers as well. 3 squared times 7 squared, that number on the right is 441. So it'd be very difficult to go about trying to find the factor pairs of these numbers, so a much faster method. For the lowest common multiple, we can use exactly what we've already done above in regards to highlighting the numbers, except, and if I do this in a different colour, as well as the 3 times 3 times 7, which I'll write down just here, 3 times 3 times 7, we also now have to multiply by all of the numbers that aren't highlighted. So if I underline them, we have a 2, a 2, a 3, a 3, and another 7. So when I've done my 3 times 3 times 7, I also have to do times 2, times 2, times 3, times 3, and there was a 7 in the other number, so times 7 as well. Now clearly that's going to give us a very large number, and considering one of the numbers was 441, we know that we're going to get quite a large lowest common multiple here as we're going up in those times tables, and the other number was even bigger. So let's times these all together. 3 times 3 times 7 times 2 times 2 times 3 times 3 times 7, and that comes out as 15,876. So definitely not one that we'd want to sit writing down the multiples of those numbers. Now, during this topic here, you might have noticed, of course, that sometimes your numbers are going to be given to you as whole numbers. So you can always write them as a product of prime factors. So for example, this number here, which was 441, if you type that into your calculator and press equals, you can use the factors button to turn that into a product of prime factors. Now typically you have to press shift and then the time button, it will say fact just behind it, and that will convert a number into a product of prime factors for you. So you can always use this method even if you are given whole numbers. But there we go. If you're not sure how to use that factors button to get the number as a product of prime factors, I will link the calculator video in the description so you can have a look and see how to do that. So this next question is looking at the mean from a grouped frequency table. So it says that there are 80 children. If it doesn't say that, we can get the 80 by adding all of those together. But to find the mean, and it's a relatively long process, we have to multiply all these rows across. Now when it's a grouped frequency table, we have to use the midpoints of the groups. So if it was just a whole number there in the height section, then we would just multiply across. But as we have a group, we need to find the midpoints. So in between 130 and 140 is 135. And if you just have a look, all of these groups go up in tens. So all the midpoints are going to be relatively quick for us to find. You just need to double check and see if there's any that have an uneven interval. Like sometimes this last one here, maybe it goes up by 20, so 170 to 190, for example. So just be really careful you don't chuck these midpoints in too quickly, and you do actually check those. So if we multiply these across, and I'm going to use a calculator for each one, so we get 540 when we do 135 times 4. 11 times 145 is 1595. 24 times 155, 3720. 165 times 22 is 3630. And then 19 times 175 to finish this off, 3,325. So to get the mean, we just need to get the total of this column and then divide it by 80. So there are 80 children. So if we add these up, 3630 plus 3720 plus 1595 plus 540, and that is equal to 12,810. So the overall estimated total height is 12,810. We need to divide that by 80. I'm going to write it as a fraction. So divide by 80, and that comes out as 160.125. And always check with your average here, particularly for the mean, that the answer makes sense. It has to be within the range. If you look at the table, nobody was outside of the smallest height, 130, and the largest height, 180. So it has to be between there somewhere. If you get an answer which was in the 200s, you know your answer's gone wrong and you need to go back and double check. And typically it's just adding up on a calculator and accidentally pressing an incorrect number or something like that. But there we go, there was our mean, 160.125. Part B here wants us to draw a frequency polygon. Now, frequency polygon is probably one of the nicest graphs to draw, particularly if we've just done the mean, because you plot the midpoint, which we've already done here, against the frequency. So all we need to do is plot these midpoints against those frequency numbers. It's a bit awkward because I have to keep scrolling up and down, but 4 on 135, so that goes up to 4. Just check the scale, it does go up in ones for each square. Then we have 11 and 24 on those midpoints again. So 11 and the other midpoint, 24. And then our final two are 22 and 19. So 22, which is just here. And then 19, which is just one below that 20. There we go. So for a frequency polygon, you have to join these together using a pencil and a ruler. And we just go dot to dot from the first point to the last point. And there we go. Really nice and easy to draw. Absolutely essential that you use a ruler for this. It cannot be a curved line. And there we go. There is your frequency polygon. On to our next question. So we have some solving inequalities, and we also have drawing that on a number line. So for this first one, when we are solving an inequality, we are looking for that smallest value of x. Here it's a negative 2y, as we're looking at y's in this one, not x's. So the smallest value is the negative 2y. To get rid of that from the right hand side, this time we'll have to add 2y, which is a little bit different to when it's a plus 2y over there. Of course, we'd have to subtract that. We're going to add 2y to both sides. That's going to get rid of this negative 2y, and it turns that 3y into a 5y. So 5y plus 6 is less than 41. We want to isolate the y, so we want it to be y is less than, so we need to get rid of this 6. So if we minus 6 from both sides, that's going to get rid of this plus 6 and get us closer to that. So 5y is less than 35, and then we can finish this off dividing by 5, because we want to know obviously what 1y is equal to, or less than. We get y is less than 7. And there we go, that's our final answer, y is less than 7. Part B here wants us to draw a different set on the number line. So for this one, we have this x in the middle as well. So we want it to be just x on its own, but we have x plus 3. So in order for it to be x on its own, we need to get rid of this plus 3. So we need to subtract 3, which will get rid of this plus 3 here. Now when we subtract 3, when it's a double inequality like this, we have to subtract 3 from both sides. So the negative 2 goes down to negative 5, being careful with your negatives, and the 4 goes down to 1. Now from there it's relatively simple, because we just have to draw a circle above both of those numbers and connect it together. However, you do need to have a look and just see if either of the inequality symbols have that additional line underneath, and we do. This one on the 1 here on the right has the extra line, so that one just needs to be coloured in. And there we go, that is our inequality on a number line. On to our next one. So this question says, in a diagram, A, B, B, C and C, D are three sides of a regular polygon, polygon P, so we can only see part of the polygon. Show that polygon P is a hexagon, and you must show your working. Now, when we are looking at these polygon questions, we can have regular or irregular polygons, and the process is relatively similar in the sense that we need to find the sum of the interior angles. Now to do that, we have a formula, so we have n minus 2 multiplied by 180, and then if it's a regular polygon, we'll divide by n as well, where n is the number of sides. So if we first do that for this 12-sided polygon, we'll be able to find one of these angles here, because we want to have a look at these angles around a point, because angles around a point all add up to 360, and these are all slotted together. So if we find first the interior angle in the 12-sided polygon, we can then look at the angle in the square, which is just a 90-degree right angle, and then we can find out what's missing for polygon P and see if it matches a hexagon, and a hexagon has 6 sides. So let's first do this 12-sided polygon. So we will have 12 take away 2, which is 10, times 180, and you can work that out first if you want, or you can type this all in as a fraction, but 10 times 180 of course is 1800, and then we need to divide that by 12 as the shape has 12 sides, so we'll do that all on the calculator, and that comes out as 150 degrees. So that is the interior angle just here in this 12-sided polygon. So to find polygon P, we want to know what's missing. We've got this angle here which we can find. So if we first add together the 90 and the 150, that adds up to 240. And we've already said the angles around a point have to equal 360. So 360 subtract that 240 is equal to 120 degrees. So whatever shape that is, whether you know a hexagon or not, it has to have an interior angle of 120. So if we want to show that, because it does say show that, if we want to show that it's a hexagon, well, we need to work out the interior angle in a hexagon. So a hexagon has 6 sides, so if we choose our formula, it would be 6 minus 2 times 180, and then divide that by 6. Now, you can type that in steps if you want. That comes out as 720 on the top, divided by 6, which does come out when you divide that as 120. And that's good. It did say show that it's a hexagon, so it's not asking us to prove it's a hexagon or sort of, say what shape it is. It is telling us it is a hexagon. So here we go. We've showed that it's a hexagon. we have our missing angle of 120. We've got our working out to show that a hexagon's interior angle is 120, and we've shown, therefore, that it must be a hexagon. And there we go. There's our angles in polygons question. Just remember, if it is an irregular polygon that you get, you just don't have to divide by 12 or divide by 6. You would just get the total and then find out what's missing in terms of the angles that you are given. So, next question. So, here we are drawing a quadratic graph. So, in this question, we are going to plot this graph, and it's also asking us to find some solutions to that graph. Now, I'm going to use table mode for this question. And again, I'll link the video in the description for this. So if you don't use table mode, you can have a look and see how I go about doing it. Just getting a calculator to give me all the answers relatively quickly. If you don't use that method though, we can find the points by subbing in the x-coordinate into the equation that we are given. So here with an x-coordinate of 3, we can do 3 squared, take away 3, and then take away 6. And you can type that all in on the calculator. And you can do that for each row or each column until you get each number, but I just prefer just to type it all in and have it all given to me. So I'm just going to type in x squared minus x minus 6 into my calculator, and the starting number is negative 3, the end number is positive 3, and it goes up in steps of 1s. So just reading these numbers from my calculator, we have 0, negative 4, negative 6, negative 6 again, negative 4, and 0. And there we go. But of course, you can just use this substitution method. Putting all the numbers in, just be really careful when you substitute the negatives in, because with the negative numbers, you do need to put negative 2 in brackets when you square it. So negative 2 squared on the outside of the bracket. Then you have take away negative 2 minus 6, and it does start to get a little complex in the way that it looks. So I do really prefer this table method. But let's plot these points. So we have negative 3 that goes to 6. Negative 2 is on 0. Negative 1 is down at negative 4. So negative 4 down here. 0 down at negative 6. 1 also at negative 6. And then it just sort of mirrors back up. So negative 2 is negative 4. And 3 is on 0. And there we go. So we do need to actually draw this in. We need to connect it all together using a nice smooth curve. Now this particular graph here, we don't use a ruler. So we are going to do a nice smooth curve, just making sure you go through the points. Most important part here is that we actually get through every single coordinate. Obviously I just need to curve that up to that first point as well. There we go, and it makes this really nice U shape. And there we go, there's our quadratic graph. Part C here says to use your graph to find estimates to the solutions, and it gives us the graph equation here, but then it's equal to negative 2. Now, it could have equals 0 there. If it was equal to 0, that'd be really nice for us to find, because all we're looking at is ground level at equals 0. We'd be looking at these two coordinates here. So if it said equal to 0, our answer would just be negative 2 and 3. But this one here has asked us to do it at negative 2. Which just means almost like dropping the x-axis down by 2. So we're going to look at a new line, which is across here at negative 2. So we just want to draw that line in, and then we're going to read the x values on this part of the curve instead at negative 2. So you'd want to get your ruler and do this as neatly as you can. Don't forget you are only finding estimates, and everyone's graph is going to be slightly different, so there's going to be a bit of a range that you're allowed here. So I just need to read these numbers very carefully. It can get a bit awkward on the negatives as well, because it's quite hard to see these squares, but 1, 2, 3, 4, sort of mark along halfway so you can see where you're at. 1, 2, 3, 4, 5. There we go. So on the right there, that one is just past 2.5, so that is 2.6. And on the left, that's again just after minus 1.5, so that'd be minus 1.6. There we go, and there's my two solutions at negative 2. So all I'm going to do is write down those two numbers. So it's 2.6 and negative 1.6. There we go. And if you're doing this on a piece of paper, you might get ever so slightly different answers to me, but they're going to be pretty close to those two. And there we go. That is finding those solutions at a line that's different to the x-axis. Okay, on to our next question. So it says here we have a gold structure in the shape of a cylinder. It says the cylinder has a radius of 15 and a height of 43. The density of gold is 19.3 grams per centimetre cubed. Work out the mass of the structure and give your answer to 3 significant figures. Okay, so to work out mass, for starters we're working with density. So you need to write out your density formula. So density is equal to mass divided by volume. You can rearrange that formula for mass if you like, or it might be that you use a formula triangle. If you do use a formula triangle, just make sure, of course, you get those letters in the correct place. You have density is equal to mass over volume. So to work out the mass, which is what we're working out here, we're going to need to do the density multiplied by the volume. Now, we have the density, 19.3, as long as it's in centimetre cubed, and we're going to multiply that by the volume, which we don't know, so we need to work out the volume. Now, the volume of any prism, you get the area of the cross-section, which in this case is a circle, and you multiply it by the distance that it passes through the shape. In this case, it's the height. So to work that out for a cylinder, the area of a circle is pi r squared, and then we need to multiply that by the height. So all we need to do is put the pieces in place and it will give us our volume. So we have pi multiplied by, this question has given us the radius, 15, so times 15 squared, and then times 43. We're obviously going to get a very large number here because 15 squared is going to be a large number as it is. So pi times 15 squared times 43. As a decimal, that comes out as 30,394.90892. And there we go, that is the volume of the cylinder. We could label that as centimetre cubed if we want there, as it's in centimetres. So we now have all the pieces, we've got the volume, we were given the density, so to work out the mass, I just need to do 19.3 multiplied by that long number up there, which I'm going to leave on my calculator, so I don't have to keep typing it in, but 394.90892. So on my calculator, I'm just going to press times 19.3, and there we go, that comes out as 586,621.7422. And there we go. So that is our mass, and that is in grams. And again, it says grams in our density units there, so just pinch it from there. So we have the grams. So it wants the answer to 3 significant figures. So 1, 2, 3, we'll chop it after the 6 here. Anything after that will turn into zeros. We just need to be careful. After the line, it is a 6, so it's going to round that up. So instead of 586,000, it's 587,000, and then everything else is just a 0. We don't need to put the 0.0 or anything like that. We've just rounded that to 587,000, which has 3 whole numbers in there, and the rest are zeros. So 587,000 grams. And there we go. Now, of course, you could be asked to do things like convert that into kilograms as well. So not forgetting there's 1,000 grams in a kilogram, but this one here did have grams on the dotted line, so we're leaving our answer in grams. Okay, next question. So Connor invests £200,000 in a savings account for 4 years. The account pays compound interest at a rate of 1.5% per annum. Calculate the total amount of interest Connor will get at the end of 4 years. So looking at this question, we have 1.5%. Now, if we add 1.5% onto our original 100%, so 100% plus 1.5%, we of course get 101.5%. Now, if we type that into a calculator, so 101.5, and then press your percent button, which is down normally at the bottom of a calculator if you're using a Casio, behind the answer button, so you have to press shift answer, and press equals, it will give you a fraction, but if you convert that into a decimal, it gives you the multiplier that we need to use, so 1.015. So that multiplier there is exactly what you do to increase by 1.5%. So if we want to work this out, we now just need to do 200,000 multiplied by 1.015. You can actually just multiply by the 101.5% as well. It will do the exact same thing as they are the same number. So 200,000 times 1.015, that'll increase for 1 year. We want to increase for 4 years. So for 4 years, I need to put a power of 4 with my multiplier, or just multiply 4 times and write them all down. It's up to you. I obviously just prefer to write the multiplier with it a lot quicker. So 200,000 times 1.015, and then that is to the power of 4, and that gives me a final amount of 212,272. And there we go, and that's 0.7101. Now, when we are dealing with money, we only want this to the nearest penny, so I'm going to chop it off after that 71 pence. You can, if it rounds up, you could argue that it rounds up, but with money situations like this, you could also argue that you're not going to get that additional penny if it did round up. Now, this one doesn't round up anyway, so we would leave it as 71 pence. Now, this question here does say to calculate the total amount of interest that Connor will get. So we've got to be extra careful here, because actually it wants us to subtract that original £200,000 just to see what the extra amount he got. And you can probably see that sort of visually without using a calculator, but just type it in, just make sure we get this bit correct. It comes out as £12,272.71. So there we go, that's the total amount of interest, £12,272.71. And there we go. There is our compound interest question. On to our next one. So in this question, we have some probability from a table. It says here there are only blue, green, red and yellow counters in a bag. Olga is going to take at random a counter from the bag, and the probability, and we can see this in the table now, it shows us blue and yellow. So it says the number of red counters in the bag is 4 times the number of green counters in the bag. Complete the table. So probabilities in a table all have to add up to 1. So to start with, we just want to see, well, what do these currently add up to what we already have? So 0.4 plus 0.15, that adds up to 0.55. So if we subtract that from 1 take away 0.55, that leaves us with 0.45 left over. Now that 0.45 is spread between these two boxes, but it says 1 is 4 times the number of green. So red is 4 times the number of green. Now when you're given that kind of statement, one being 4 times the size of the other, that can be written as a ratio. So we can write it as red to green. Red is 4 times the other, so that is the ratio 4 to 1. So all that means is we have a decimal that is going to be split in the ratio 4 to 1. If you prefer, you can write that as 45%, if you prefer to use a whole number, but ultimately we need to do 0.45 divided by 5 parts. So divided by 5, that comes out as 0.09. And again, you can just do this on the calculator. So we're just going to multiply both of these by 0.09. That gives us 0.36 and 0.09. And there we go. There's our 2 parts. Just make sure we put those in the correct place, because I've got red on the left and green on the right, and in the table green's on the left. So just be really careful. This one is my 0.09 for green and 0.36 for red. And there we go, they all now add up to 1, and the probability of red is 4 times the probability of green. And there we go, that's our final answer. So using a ratio within a probability table. So for question 10, we have an error interval. It says here, Oscar rounds a number x to 1 decimal place, and the result is 7.2. Write down the error interval. So 7.2 is in between as a single decimal place number. It's between 7.1 and 7.3. When we're looking at an error interval, we are looking at those cutoff points in the middle. So it can help if you prefer to add a 0 onto these, if it helps you to visualize it. But we get 7.15 and 7.25. And there we go. That gives us our upper and lower bound. So 7.25 and 7.15. And not forgetting, if you have a question that mentions bounds or anything that's been rounded to 1 decimal place and you're asked to work out an upper or lower bound, you need to write down these error intervals on those questions for any number that you are given. But there we go, just an error interval there for this one. Okay, our next question, we have some right angled triangles. It says here ADC and DEB are straight lines. A to D is 4.4 centimetres, B to C is 8.6. That's all given to us on the diagram, and then it tells us E is the midpoint of DB. So this one here, that does split it in half. So this is half and half, just here. And then it tells us a right angle and a 40-degree angle, which we can see in the diagram. Work up the size of angle EAD, and we want it to 1 decimal place. So E to A to D is this one here, let's label it X. So that's what we're trying to find. Now at the moment, if you look at that right angle triangle, so this one just here, we can't work that angle out straight away because we need at least 2 sides or at least another angle in there. But ultimately we're going to need 2 sides if we're going to use trigonometry, and we're going to use SOHCAHTOA, which is what this question's about. We might have Pythagoras in there, but we might not, so let's just have a look and see. So in order to work out this side here, let's label it with a Y. We could do that using this big triangle on the right, BCD. We could work out the opposite side to the angle, and then whatever answer we get, we can cut that in half or divide it by 2, as E is the midpoint. So if we label this up, this is the opposite side, and we've been given the hypotenuse, so we can use our sine formula. Again, if you use formula triangles, SOH. So to find the opposite, we would cover up the O, and it's sin 40 multiplied by the hypotenuse of 8.6. So there we go, sin 40 multiplied by 8.6, not forgetting to close your bracket, or you can write the 8.6 first, and that gives us 5.52797, a few more decimals there, but we are going to divide this by 2. And if we divide that by 2, it's going to give us the length of E to D, which is 2.763986. There's quite a lot of decimals here, so I'm going to stop there because it does only want my answer to 1 decimal place. I'm going to label this though on the diagram, and that is 2. Let's just round it to 764. It wants it to 1 decimal place, so I'll leave it to 3 in my working out there. In fact, I'll just leave the whole number on my calculator as well. So there we go, we're pretty much there. I can now look at this smaller triangle on the left hand side. We need to work out an angle now, so I'm going to label this up again for trigonometry. So that is the opposite side, the 2-point number that we're looking at, the 2.7. So that's my new opposite side, and we don't have the hypotenuse, so this is the adjacent here now. So to work out that angle, O and A, we'll use our tan formula, so TOA. We are working out an angle, so I would cover up the T, and when I'm working out an angle, I need to press Shift tan first, so I get tan minus 1, and then it's the O divided by the A, so 2.764 divided by the adjacent, which is 4.4, and there we go, typing that into the calculator, that gives me an angle which comes out as 32.136, and a few more decimals, but I'm going to stop there because again it does want my answer to 1 decimal place. I've got enough information for that, so 32.1, it was an angle, so 32.1 degrees. And there we go, 32.1 degrees is my final answer, 32.1. Okay, on to our next question. So question 12 here, we have an enlargement with a negative scale factor. So here it says enlarge the triangle by a scale factor of minus 1.5, centre 0, 2. So 0, 2 is just here, and an enlargement of negative 1.5 means it's going to get 50% bigger, or 1.5 times bigger if we multiply the sides by 1.5, and it's going to go in the opposite direction. So when we count to each vertex on the shape here, if we think about this as being 1, 2, 3, 4 to the right, well, 4 multiplied by 1.5 is 6, and as it's negative, we just go the opposite way. So if it was positive 1.5, we'd just go another 2, because that would make it 6 in total, and we draw a new point in there, and then draw it in 1.5 times bigger. A negative enlargement, we just got to take it a little slower though, so I need to go 6 to the left. 1, 2, 3, 4, 5, 6. And there we go, that's my first vertex done. Now, when you're doing a normal positive scale factor, it's quite nice at this point because you can just draw the shape in, 2 times bigger or 1.5 times bigger or whatever scale factor you've been given. But with a negative scale factor, we do just need to go a little bit slower. So I'm going to pick another vertice and see how I get there. So to get there, I have to go 1, 2 up and 1, 2 right. Now 2 times 1.5 is 3. Again, you can type that in on your calculator. So instead of going 2 up and 2 right, I need to go 3 down and 1, 2, 3 left. And that will just end up there. Now you can probably see where that last point is going to go now, but I never like to just rush and guess at this point. So I am going to do the final coordinate as well. This one just up here. Now to get there, and I'll get rid of some of these lines now so we can sort of draw this on the screen. You obviously don't necessarily need to draw these in. I do find they help, but there we go. I'll do the last one. So 1, 2 up, 1, 2, 3, 4 right. So I need to go 3 down. So 1, 2, 3, and that was 4 to the right. Times that by 1.5 is 6. So 1, 2, 3, 4, 5, 6, and there is our last coordinate. And there we go. So from there, I obviously need to join these points up using a ruler and a pencil. Particularly these ones with a negative scale factor, do take a bit of time. So do make sure you join these up really nice and clearly. There you go. Make sure it's drawn nice and neat. And there you go. There is your enlargement with a negative scale factor. And there we go. On to our next question. So we have an algebraic fraction here. It says write 5 over x plus 1 plus 2 over 3x as a single fraction in its simplest form. So in adding or subtracting any type of fraction, we need a common denominator. So here, if we have 5 over x plus 1, add 2 over 3x, we need to multiply the left side by 2x and the right side by x plus 1. So if we do that, the left fraction becomes on the top there. That should be 3x, not 2x. There we go. So 3x. The numerator becomes 15x. And the denominator, which would make a single bracket, it would make this bracket here, 3x lots of x plus 1. There we go. So that would make 3x squared plus 3x. We're going to add to that. Again, this would make a single bracket on the numerator, 2 lots of x plus 1. So that would make 2x plus 2 over 3x squared plus 3x. We now have a common denominator, so all we need to do is add these together with 15x plus 2x, which is 17x, and then we have the 2, so plus 2, and that's all over 3x squared plus 3x. And there we go. Now we do need to have a look here. It did say to write it in its simplest form, however it is only a 2-mark question. I'm not going to assume it doesn't simplify, but we need to have a look and think if it simplifies now. Now if you look at the numerator cannot factorise. There's nothing that can come out of that. The denominator does, because we only just expanded it. So if I could factorise it and write it as 3x brackets x plus 1, which is what it was before we expanded it out, and I can write it factorised as well. However, the top and the bottom don't divide by anything, so it doesn't simplify. So actually that's my final answer. So 17x plus 2 over, and then we have either the factorised version or just 3x squared plus 3x. Either would be fine in that question. But there we go, a nice little 2-mark algebraic fraction. Okay, question 14. Ellie wants to work out an estimate for the total number of fish in a lake on Friday. Ellie catches 180 fish, she puts a tag on each, and on Saturday she catches 305 and 45 of them are tagged. Work out an estimate for the total number of fish in the lake. Now there are a couple of different ways that you can approach this, and there is kind of like a little formula-ish approach that you can learn as well. However, it is just about proportion, and it's just looking at 2 fractions and just writing them equivalent. So I quite like this topic. It's called capture recapture. So here we catch 180 fish in the first capture. Out of, we don't know. This is the whole concept. We're trying to find out what the total is. And the next time we do a second capture, we have 45 that have the tags on out of 305 that were captured. So there's capture 1 and capture 2, the capture recapture. So what we want is for these to be equivalent to one another. Now to make them equivalent, all we have to do is have a look and think, well, how do we get from here to here? From 45 to 180. So all I need to do is 180 divided by 45. That comes out as 4 on the calculator. So we know we multiplied by 4. I just do the same to the denominator, to times by 4. So on my calculator, I'm just going to do 305 times 4, which comes out as 1,220. And there is my estimate for how many fish were in the lake. Now obviously that estimate there, we've not been asked it in this question, but that estimate does depend on a few things. So we assume things like the same capture method was used. We assume that none of these tags have come off in between the captures. Obviously those sorts of things would affect the answer there. If lots of the tags had fallen off, obviously that would be affecting our answer. So there we go, 1,220. On to question 15, we have a circle theorem. So it says here, A, B and D are points on the circumference of a circle. EDC is a tangent, which we could see. BDC is equal to 57, so B to D to C. So it's telling us this one here is 57 degrees. And there we go, 57 degrees. And what else does it tell us? It also says, find the size of angle AOB, and you must give a reason. So AOB is this angle here. Now, there are two circle theorems that I can see in this question. We have the tangent to a radius, as we have O to D being a radius there. So there's a tangent to a radius, which makes a 90-degree angle. And we also have what I call a cyclical triangle, a triangle which is at 3 points and connected to that tangent, which is the alternate segment theorem. So there's a couple of circle theorems that we can apply here, and actually I think there's two routes that we could take to get our answer. Now the first route, which is quite a nice one, is we could find this angle here because a tangent meets a radius at 90 degrees. So I can do 90 take away 57, which tells me this one here is 33 degrees. Now I would label that. You can label it by the diagram or down below, but I would just write here 90 minus 57, which equals 33, because a tangent meets a radius at 90 degrees. There we go. And there's our reason. Now the next part, we need to sort of think about the diagram here. So we have a few different triangles that are given to us. Now this triangle that we are currently within, this one here, and this length here, both of those lines that I've highlighted are both a radius, which means they are the same length, which means that's an isosceles triangle, which means the 33 is also over here. So this one's also 33. So obviously that's another reason that we need to give. So this one's 33. They are called the base angles. So base angles in an isosceles are equal. There we go, are equal. And that's why that's 33. We can now find this missing angle in the triangle, just here. So we can add together 33 add 33 and take that away from 180. So 180 take away 66 is 114. So this one here is 114. We've already written down quite a lot of reasons here, but it does say give every reason. So I'm going to give every reason. So this one here was because angles in a triangle sum to 180 degrees. You can add up to 180 degrees as well. And then we can finish this off because next to that we have two angles on a straight line. So this is obviously a straight line here. Angles on a straight line equal 180. So we can finish this off. 180 minus 114, which we already worked out, is 66. And there we go. Our final answer is 66 degrees. And that final one there, angles on a straight line equal or sum to 180 degrees. Now that's one way that you could have done it. You might have spotted there's another way. So we'll just discuss another way as well, because this was quite a good question. Actually, what you could have done, and I'm going to highlight over the top of this, I'm not going to rub it all out, but you could have found some of the angles using the alternate segment theorem. So with the alternate segment theorem, if we go across the tangent, up the other line to this angle here is the same as that 57. So that's 57. This is another isosceles, so this is 57 as well. And if we add together 57 plus 57, we get 114. Take that away from 180, as it's angles in a triangle, and we'd have got our 66 as well. So in that one there, we'd have had probably one less step, so it might have been a slightly faster route. So we had the alternate segment theorem to start with, we then had base angles and isosceles are equal, and then angles in a triangle sum to 180, so we just wouldn't have had to do the angle on the straight line part to finish it off. So ever so slightly less steps if you go that route. Either way is absolutely fine. But there you go, a couple of different ways that you could approach that question. That's what I like about circle theorems, there's always normally two ways of getting the answer. Okay, so there we go. What was our final answer? Let's write it down there. So our final answer was 66 degrees. And there we go, 66 degrees. Okay, so for this question we have some iterations. Iterations is definitely a calculator exclusive topic here for this one. We need to substitute this in. So all I'm going to do is write on my calculator how I'm going to type this in. So we have our iterative formula, -2, take away 4 over the current x value that we're using squared. So it says start with -2.5, so a bit of an awkward one to start with. So to find x1, all we're going to do is sub that into our formula. So we have -2, take away 4 over, and as it's negative, we do need to put it in brackets, so -2.5, close bracket squared. I'm just going to type that in on the calculator. So -2, take away 4 over, in brackets, -2.5, close brackets squared. And that comes out as -2.64. Now, when I do this, and again, I'll link the video to how I approach iterations on a calculator using a few little calculator tricks as well. But here, I now just need to replicate the exact same formula, except in the bracket, I want my new value. Now, -2.64 is not a difficult number to go and retype back in. And if you use the left key on your calculator, you can just go delete it and type your new number in. However, at this point, I like to use the answer button. So I'm just going to use the answer button, which puts my previous answer in. You need to be really careful you haven't clicked anything on the calculator and you haven't got a second answer in there. So just be really careful you don't type anything in. And then just press equals again. I'm going to press equals again. This time I definitely get a number I don't want to type in, but I get -2.573. Let's have a look. 3921028. And actually on my calculator there's a big recurring version of that, but if you press the conversion button, there should be a time where it cuts off at around 7 or 8 decimal places. How many have we got here? 1, 2, 3, 4, 5, 9 decimal places there. So I'm going to use that version because not all calculators will give that recurring value, so it's fine to write that one down. I've got one more left to do, so x3. Again, at this point, because I've used the answer button, all I need to do is press equals again. I'm going to write down all the steps of working out, though. It's not too difficult to write that down again. Press equals again. And here we go. I get my final answer, -2.603767,255. And there we go. There are my 3 values. It probably wants me to write this down the bottom. Right, I'm not going to rewrite those all again. But obviously, you could write those final answers straight onto the dotted line when you are done. But there we go. There is some iterations. These answers that we are getting here are estimations to a solution to an equation. Now, we've not been given the equation in this one, and sometimes you are asked to sort of prove solutions are in between 2 numbers, and you have to sort of sub those numbers into the equation. But these are estimated solutions towards that equation. Okay, we're not given that in this one though, we're just asked to use it. So there we go, there's the values of x1, 2 and 3. Okay, question 17. We have some similar shapes. So straight away at the start it says he's going to make a clay statue that's mathematically similar to a clay model. It says the model has a base area of 6 centimetres squared and the statue is going to have a base area of 253.5 centimetres squared. Mark uses 2 kilograms of clay to make the model. Clay is sold in 10 kilogram bags. Mark has to buy all the clay he needs. How many bags is he going to need? Well, to start with, we are going to need to find the volume scale factor if we're looking at the clay. So at the moment, we've been given two numbers which are an area or a surface area of the base. So if we find the area scale factor, we would want to do 253.5 divided by 6. So 253.5 divided by 6, that gives us an area scale factor which comes out as 42.25. So when we are moving between scale factors, I'm going to write surface area is 42.25. I then need to find a linear scale factor, so length and then volume, or area, length and volume. So to get to volume, I have to first go down to length, and I do that by square rooting. So I'm going to square root 42.25, that's going to give me a length scale factor, and that comes out as 6.5. So 6.5 is for the length, and then to get to volume, we need to cube that. So I'm going to do the cube of 6.5, so 6.5 cubed, and that comes out as 274.625. So the volume scale factor is 274.625, meaning that the real one that we are, the actual statue that's getting built here, is going to be 274.625 times bigger in terms of its volume. So it said Mark used 2 kilograms of clay to make the model, and that's just here. So we're going to need 274.625 times that. So 2 times the volume scale factor, 274.625, and that gives us a volume for the real statue, which comes out as 549.25. So 549.25 kilograms that's going to be needed. Now it says here, clay is sold in 10 kilogram bags. How many bags of clay will Mark need to buy? Well, if it's sold in 10 kilogram bags and he needs 549.25 kilograms, he's going to have to buy just over, because it only comes in the 10 kilogram bags. So if we divide by 10 on the calculator, there we go, and actually we divided by 10, so that's quite a nice one, 54.925. That means he needs 54.925 bags. Of course, it's only sold in 10 kilogram bags. He needs to buy enough, so we'll round that up to 55 bags. And there we go, that's going to be our final answer there. He's going to need 55 bags, and that was converting through some area, length and volume scale factors. Not forgetting, if we were given the volume and for whatever reason had to work out the area, instead we would have had to have cube rooted and then squared the length scale factor to get to area instead. But in this one we were given the area, so we had to square root and then cube to get to that volume scale factor. Okay, so there we go, final answer was 55, so 55 bags as our final answer. Okay, next question. So it says here is a speed time graph for a train. The graph gives information about the speed, v meters per second, of the train, t seconds after it starts to move. So there we go, there's our graph that we're given. It says work out an estimate for the distance the train travelled in the first 20 seconds and use 4 strips of equal width. Now these ones are always a bit of a pain because the numbers are quite hard to read, but we need to find the area under this curve. So for the first 20 seconds, 4 strips of equal width, each one will go along at 5. So we have 5, 10, 15, 20, 4 strips will work. So when we do this, nice straight lines going down, hoping that these points land on relatively nice numbers where we can read the heights. And there we go, there's our last one. So we need to work out the area of these shapes, which means we need to sort of join them all together and create the actual shape. So we have a triangle, then we have a trapezium, then we have another trapezium here, and another trapezium to finish it off. So to work out the area of a trapezium, you take the parallel sides, add them together, halve it, and times by the distance between them. So let's get the sort of base lengths here. We have a 5 as the base of this triangle, and all of these are 5. So there we go, at least they're all 5. We just need to get the heights of each of these lines just so we can properly work out the area. So I'm going to draw some lines across so that I can read these heights a little better. Actually, and some of them land on some relatively nice whole numbers, so that's always good. This one does not. There we go, we'll see what that comes out as. And there we go, let's just label these so we've got all the heights. Just check the scale, it does go every 2 squares is 1, so that's 2. Just double check, 3, 4, 5, yep, that works. So the next one is 5, the next one is 10, and that final one up there is 16, 17, 18. There we go, so I'm going to label these on the diagram as well. So that's 2, 5, 10, and 18. And now we just need to work out the area of each of these shapes. So the triangle, we're going to do the base times height divided by 2. So 5 times 2 divided by 2, that gives us an area of 5. I'm going to label this in the diagram. You can write it just down below. I'm just going to label them in here to start with. So that's an area of 5. For the first trapezium, we have add the parallel sides. So 2 plus 5 is 7, divided by 2, and then times it by the distance between them, which is 5. So we have 3.5 multiplied by 5, and that gives us an area for that one of 17.5. Doing the same for the next two, same process, so 5 plus 10 divided by 2 times by the distance between them. So that's 7.5 times 5, which comes out as 37.5. And then we're almost done. Final one, final trapezium. Add together the parallel sides, 10 plus 18 divided by 2 times by 5. And there we go, let's work that one out. So 10 plus 18 is 28, divided by 2 is 14, times by 5 gives us an area of 70. So there we go, there are my 4 areas, those areas representing the distance. So we need to add them all together. So 5 plus 17.5 plus 37.5 plus 70. And there we go, we'll just add these together on the calculator. Plus 17.5 plus 5, and that comes out as 130 metres. That seems like quite a lot of working out on these questions here, but it is just working out a trapezium and a triangle. Really, when you join it up, you are just working out the area of a triangle and a trapezium, but it's all about accuracy. So do use your ruler to go along and measure the heights of each line, just to make sure that you get as accurate a reading as possible for those areas. There we go, there's the distance travelled. This next part says Claire finds the gradient of the graph at t is equal to 1.25. Describe what Claire's answer represents. Now, 1.25 is obviously going to be very, very low. So just down here, 2.5, 1 point is just down here. So that'd be very difficult for us to work out the gradient at that point. But if we did work out the gradient, and let's imagine we've worked out the gradient at a different point. Just imagine just up here, I can't really draw over the top of the lines, but if we worked out the gradient at t equals 15 just here, we would draw a tangent in, we would then go across and up, we'd work out a rise and a run. Ideally, we would get a run of 10, so the change in x over change in y. And when we do that, it tells us the rate of change of these two things. Now, in the case of speed and time, the change of speed over time is to do with acceleration. So this is going to represent the acceleration at that point. However, you can have other types of graphs like this where you have distance and time, and that rate of change is about the speed, the change of distance per second. So this particular one is a speed time graph. So the tangent at a point there tells us the acceleration. However, just bear in mind if there is a distance time graph, then that rate of change is the speed. So here we go, describe what Claire's answer represents. It represents the acceleration. There we go, I'll just put the acceleration at t equals 1.25. And there we go, there is our answer. Okay, on to our next one. We have some graphical inequalities. Now you can use table mode for these particular line equations as well, but I'm going to use a relatively quick method for plotting these graphs using the y-intercept and gradient method, where I just plot my first point on the y-intercept, and then I'm just going to follow the pattern for the gradient. But you can use table mode for these to plot all your points and make sure these are nice and neatly drawn. Now it says to label the region R that satisfies all these inequalities. So to start with, I'm going to plot that first line, which is going to be y equals a half x minus 2. Now just paying attention to the symbols in the inequality as well. If we don't have the additional line underneath the inequality like this, then we are going to do a dotted line for these particular ones. So we're going to draw a dotted line as well when we join these together. So a half x minus 2 means we're going to start on minus 2. And for every jump across, we're going to go up by a half. So if we go across one to the right and up by a half, it puts us around here. And then across one and up a half puts us to there. Now you can kind of see as well that the pattern between the points here, which is probably a little bit easier when we have a gradient of a half, is to go across by 2 and up by 1, because every one across it goes up by a half. So if I go across by 2 and up by 1, across by 2 up by 1, I'm just going to replicate that pattern going the other way. So across and down and across and down. Now there is my line. I just need to draw this in using my dotted lines or dashed lines, which is always a little bit awkward because you want it to be really nice and neat. So obviously using a ruler for this, I'm just going to have to freehand it and try and make it as straight as I can. But of course you would do this with a ruler, drawing a nice dashed line. Obviously make sure these dashes, if you do have to draw ones like this, are really nice and clear because you want them to show up on the exam. So there we go. There's my dashed line for the first one. Now the next line is a nice one to draw. X is less than 3. That's just the line x is equal to 3 that I have to draw. Obviously again with my dashed line. X equals 3 goes through 3 on the x-axis, and it's just up and down from that point. So I want a nice dashed line going up right to the end of the graph, and then also going down to the bottom as well. And there we go, that's my nice one out of the 3. There we go, on to my last one. This one looks worse than it actually is. So y is equal to 6 minus 3x. Now the x and the y-intercept there, or the gradient part and the y-intercept are written the other way around. So you could write that as y equals minus 3x plus 6, if you prefer to look at it like that, which just means it has a y-intercept of 6 up here, and the gradient's negative 3, which just means every jump across, I go down by 3, so down to 3, down to 0, it's a very steep line, and then the next one is sort of overlapping one of my other lines, so down by 3, being really careful I get that in the right place, and then down by 3 again, 1, 2, 3. So a bit of an awkward one that I need to join up. I'm going to do my best to connect these together. And there we go, we've got a nice dotted line. All of our regions are now pretty clear as to where we need to find them. Our next step is just to find that region that satisfies all of these and label it R. There we go. Now to do that, I want to first look for one of the relatively nice inequalities. So that x is less than 3 is a really nice one. I'm going to get rid of these equations. So for x is less than 3, we know it has to be on the left-hand side of that line, because above that, all the x values are greater than 3, which automatically takes a load of these regions out. But it does mean we have this one here. I'm going to label them with numbers to start with. We've got region 1, this region 2, region 3 over here on the left of that line, and you've also got this little one in the middle, although there's not actually any coordinates in there that we're going to be able to test. So we're going to have to test the other 3 and see if any of them work. Now it might be that you have a really good understanding of these inequalities. Typically though, I think it's easy just to pick a coordinate. Let's go with this one here, and we'll test the coordinate 2, 2 in the inequalities. If it satisfies all of them, then that is our region. If not, we'll move on to the next one. So for the first one, y is 2, so is 2 less than? Half of 2 is 1, minus 2. Is 2 less than negative 1? Well, the answer to that one straight away is no. So region 1, out the question, it's not region 1. So we'll find another coordinate and we'll test that one. Now this has got 1, 1, that's quite a nice one there. I do try and pick the positive numbers if I can. You can't always, but I'm going to pick positive numbers for region 2. Let's check that one out. So sub it into this first one. Y is 1 less than, half of 1 is 0.5, take away 2, 1 is less than negative 1.5. The answer's no, so it doesn't even work in the first inequality, so it's not that region. Now, if it's not region 3, which I'm going to test now, let's pick this coordinate here, 2 and negative 2. If it's not that region, then we know it has to be that small region 4. But I have a feeling it's going to be this one, so 2 and minus 2. So it didn't work in the first few, let's get rid of that. Let's hope it works for this one. So 2 and negative 2, so negative 2 for y is less than, half of 2 is 1 minus 2, so minus 2 is less than minus 1. That works, but I do have to test it in all the others now. So x was 2, so is 2 less than 3? Yes it is. And for the final one, negative 2 is less than 6. Y was negative 2, wasn't it? Let's just double check. Yep, y was negative 2. Is negative 2 less than 6 take away 3 times 2, which is 6. So is negative 2 less than 0? Yes, it is. Therefore, that coordinate works in all 3 inequalities, and it must be that region down there, which I've called region 3 at the moment. But there we go. This would be the region here. There we are. Make sure that R is really nice and clear. I'm going to get rid of all this working out. There we go. I'm going to get rid of, it doesn't matter if you've labelled the coordinates on the diagram, as long as that R is really nice and clear. But I'm going to get rid of those, as I've probably written those to the side. And there we go. So there we are. There is our graphical inequality. We've labelled the region R. Sometimes it says to shade it in. This one just says to label it R. If it does say to shade it in, don't sit for ages shading it in. You can just do some little lines like this, just to make sure it's really clear. This one doesn't say to shade it in, it just says label it R. But there we go, if it did say shade it in, it'd be absolutely fine just to do it like that. And there we go, there is our graphical inequality. On to our next question. So for this one, we have some graph transformations. It says the graph of y equals f of x is shown on the grid. Graph A is a reflection of the graph y equals f of x. Write down the equation of graph A. So what we need to do is have a look at one of the coordinates. So on f of x, let's go with this coordinate here. That x coordinate is negative 2, if that's scaled as negative 1, negative 2 there. Now on the new graph, the graph of A, the x coordinate has become 2. So what's happened is the symbol has changed on the x coordinate. If the symbol has changed from 2 to negative 2, and it's a reflection of the x coordinates, then the negative has to go with the x in the bracket. So it will be f of, in brackets, minus x. If the y coordinates had changed, then you would have minus f of x, and that's outside of the bracket affecting the y coordinates. But here it's the x coordinates which have been affected. They have been reflected in the y-axis. So my equation is y equals f of minus x. There we go, which just changes the symbols in front of all the x coordinates. On to our next one. Here's the graph of y equals g of x, shown on the grid. Graph B is a translation of y equals g of x. Write down the equation of graph B. Now there are 4 different things that we can do for a translation. It can either move left and right, or it can move up and down. If it's moving up and down, it's affecting the y coordinates. So for example, if it went 2 up, we would have y equals g of x plus 2. And likewise, if it went 2 down, it would be y equals g of x minus 2. So when it's outside the bracket and it's affecting y, it's pretty obvious in terms of what those movements mean. Plus 2 goes up 2, minus 2 goes down 2. When it's affecting the x, however, which this one isn't, it is moving up and down. So when it's affecting x, if it goes 2 left, then it's y equals g of, and this is where it slightly changes. You have x plus 2 in the bracket. It does the opposite. So left you would normally expect to be minus 2, but when it's inside the bracket, it's the opposite symbol, so plus 2. And then likewise, if we have 2 right, it would be y equals g of x minus 2. So typically, when it's moving up and down, it moves towards the positive numbers upwards, negative numbers downwards. But inside the bracket, it does the opposite. So just be aware of that. Now this particular one, it's going from 0 up to 1 there. So that's just between 0 and 2. So it's gone up by 1. So this is a translation where it has gone up by 1 to get to graph B. So up by 1 is outside the bracket, so g of x plus 1. There we go, and there's our new equation where it's just gone up by 1. And there we go, there are some graph transformations where we had the reflections, and we've also talked about those translations. And there we go, y equals g of x plus 1. This next question, we have some functions. So for this one, our functions are actually in brackets. So typically we'll always want to expand any brackets. Let's expand these. The one on the right is nice and easy to expand, 2x minus 2, just timesing them by 2. The one on the left here, we do have a double bracket to expand, so I'll just do this to the side, x plus 1 and another x plus 1, and that gives us x squared plus x plus x plus 1. There we go, and that is x squared plus 2x plus 1. So there's our function of f, x squared plus 2x plus 1. This part A here says show that g(f(x) equals, and then we have a function here that we have to make it equal. So g(f(x) means we're going to do f first, and as it's an x in the bracket, it means we're going to put the entire function of f into the function of g. So when I do that, I just put a bracket around this function, a bracket around the x or any x's where it needs to go in the case where sometimes there's two x's. I'm just going to swap what's in the bracket. So that'll be 2. In brackets, instead of x, we have x squared plus 2x plus 1. And then at the end, we've got minus 2. So I just need to expand and tidy this up and hope it looks like what they've asked me to make it look like. So I've got 3 to expand, or 3 to multiply by 2. So we get 2x squared plus 4x plus 2. And then we have this minus 2 at the end. Those 2's are going to cancel each other out, so they're gone. 2x squared plus 4x. And how do I make it look like what they've asked me to make it look like? Well, I need to factorise it. So I need to take a factor of 2x out. 2x times x makes 2x squared, and 2x times 2 makes the 4x. And there we go. From there to there, we've factorised. There we go. Don't necessarily need to label that we factorised there. I've shown it just within the maths. It's quite hard to show how you factorise that, really, in that sort of last step there. I've kind of just written what they've asked me to write. I haven't really got any way of showing that. But there we go, labelling it with factorise, I guess, makes it a little clearer, but it'd be fine just to leave it without that. There we go. That is a composite function, and now we have an inverse function for g. So it wants me to do the inverse of g, but it also wants me to substitute 7 into that. So not just g to the negative 1 with x in the bracket, which is just finding the function. It actually wants me to substitute 7 in. There's a couple of different ways of doing this, but I'm going to find the inverse function. I think that's probably the safest way of doing it. So I'm going to write the function of g, but I'm going to write it with y equals, so 2x minus 2. So to find the inverse function, I'm going to make x the subject, and then just swap the x back in for that y. So I'm going to start by adding 2 to both sides to find the inverse. So we have y plus 2 is equal to 2x. And then to get x on its own, I need to divide by 2, which will create a fraction. So I have y plus 2 all over 2 is equal to x. So to make that my inverse function, I'm going to swap the x and y's back over. So my inverse function of g to the minus 1, is equal to x plus 2 over 2. Now we want to substitute 7 in. So here we are now using 7. So I just need to put 7 into my fraction instead of x. So 7 plus 2 divided by 2. And 7 plus 2 is 9 divided by 2 is 4.5. And there we go. Don't necessarily need to put equals there, but we get the answer. 4.5. And there we go. That was my inverse function and substituting a number into it. But there we go. There was some composite and inverse functions. So this next question is looking at direct and inverse proportion. So we're going to need to use some of our equations of proportion. So it says here y is proportional to x squared, y equals 3 when x is 0.5. Definitely going to need to use our calculator if we're using decimals like that. And x is inversely proportional to w, and x is 2 when w is 0.2. Find the value of y when w equals 2. Now sometimes you have to merge the equations for these together. So we'll have to see at the end, do we need to put the equations together in order to do this? So for the first one, we are directly proportional. So y equals kx squared. It says y equals 3 when x is 0.5. So put the numbers in. Y is 3, and that is k times 0.5 squared. Let's do that to the side. 0.5 squared, rather than writing it out multiple times. And that is 0.25. So k times 0.25. Well, you can write that as 0.25k. But I need to divide both sides by 0.25. There we go. And that's going to tell me my value of k. So 3 divided by 0.25 is 12. So 12 equals k. And now I can write my formula now, which is y is equal to 12x squared. There we go. And that is my first formula there. And that tells me how to find y. So there we go. There's my first one. Okay, so the next one is inversely proportional. So I need to use my inverse proportion formula. So x is equal to, instead of kw, it's now k over w. And then x is 2. So we have 2 equals k over 0.2, the number they've given me for w. To solve this, to get k, I need to times by 0.2. So 2 times 0.2 is 0.4. So k equals 0.4. And I can now write my equation again. So I get w equals 0.4. Sorry, x equals 0.4, not w. There we go, over w. So x equals 0.4 over w. And there is my second equation. There we go. Now, sometimes these questions now ask you to write a formula for, let's say, something like y in terms of w. And it does want me to find here a value of y when w equals 2. So it could have asked me to do something like that. However, that would be a pretty horrible fraction to have to put in, because what we'd have to do is we'd have to take the 0.4 over w and put it in place of the x here, which means we'd have to square it and times it by 12. And it wouldn't be too bad, but we would have to square this fraction, which you could do on the calculator, to be fair. 0.4 times 0.4 is 0.16. So you get like 0.16 over w squared, and then you have to times it by 12. And you could kind of create a new formula like that. And you could do that for this question. However, it just says find the value of y when w is 2. Well, if we put 2 into our formula here, it will give me a value of x. And then whatever that value is, I can put it into this formula. So I may as well just do that. It doesn't necessarily need me to create a whole new formula. So if we work it out for x, so when w is 2, x is equal to 0.4 divided by 2. So x is equal to 0.2. And just check it on the calculator. There we go, 0.2. Now I can put 0.2 into my first formula. Y equals 12 multiplied by 0.2 squared, as it's w squared. Just type that in, 0.2 squared, and we get 0.48. And there we go, there's my final answer, 0.48. So that was a relatively nice one in the sense that we could just put the numbers straight in and sort of work backwards through those formulas that we created. But of course, remembering you can be asked to merge these together, and just being aware of that, if it said something like write a formula for y in terms of w, well, you'd have to substitute that 0.4 over w into that other formula there in place of x. But there we go, there was some direct and inverse proportion using both forms. Okay, so our next question, we are solving a quadratic here. Now, if we are solving a quadratic, it has to be equal to 0 first and foremost. So let's first rearrange this. So plus 5x to the other side, and that gives us 6x squared plus 5x equals 6. It might be better at this point though just to subtract 6 from both sides as well if you're comfortable to do it in one step. Minus 6 equals 0. Now at this point we've got two options. We can either try and attempt to factorise this, and it might factorise, it is only 2 marks here, so it may just factorise, in which case we can get our solutions relatively quickly. However, if we are using a calculator paper, we may as well just use the quadratic formula. So minus b plus or minus the square root of b squared minus 4ac all over 2a. And if you're comfortable using the quadratic formula, it's a lot quicker. So a equals 6, b equals 5, and c equals negative 6. So I have minus b, so minus 5, plus and minus the square root of 5 squared. Typically I always put this one in brackets just in case b is negative. And then minus 4 times 6 times negative 6. And that's all over 2 times 6. Now I'm going to type that into my calculator, first using the plus symbol in front of the square root, and next using the negative symbol. So I have minus 5, I'm going with plus the square root of 5 squared minus 4 times 6 times negative 6, all over 2 times 6. Now for the plus version, I get 2/3. And if I go back into my calculator, so just deleting the plus, swapping it for a minus, I get minus 3 over 2. So there we go, there's my two solutions. I'll say x equals 2/3. I'll say and x equals minus 3 over 2. And you can feel free to write those as decimals if you like. However, 2/3 is a recurring decimal, so I do prefer to leave it as a fraction, but you could write minus 1.5 for that second one. Absolutely fine, but there we go. There's using the quadratic formula just to solve a quadratic. Now for part B, it wants us to write something in completed square form. And this is a relatively tricky one because we have a coefficient of x squared, which is bigger than 1. Now when we have this, I mean, if you're already confident with completing the square, it's not actually too bad, particularly when we have a calculator. Because we have that negative number at the end, we're going to have some decimals involved as well. Sorry, we have the odd number at the end, we're going to have some decimals as well. So before I complete the square, I need to factorise the 2 out. So when we do that, I get x squared minus 4x, and then 5 divided by 2, you have a calculator as well, 2.5. Now I'm going to ignore the 2 on the outside, almost imagine it's not there, and just complete the square for what's inside. So I need to halve the coefficient of x, so I get x minus 2 squared. And depending on how you complete the square, I tend to just think, well, if I expand this double bracket, what number would I get at the end of my quadratic? Negative 2 times negative 2 would give me plus 4. I don't want plus 4, I want this minus 2.5. So to get from 4 to minus 2.5, I'd have to subtract 6.5 to complete that squared bracket to make sure that when it's expanded, I do get minus 2.5 at the end. So I have completed the square for what's inside, and this is the point now where I have to remember that that 2 was there, and I need to reintroduce it. So I put the whole thing in a big bracket. You can use a non-squared bracket if you like, but I need to multiply the 2 back in. So when we do that, I need to multiply that whole bracket by 2, and that's really easy to do because you just put 2 in front of it. So 2 lots of x minus 2 squared, and I need to multiply the 6.5 by 2. Now it's going to stay negative. 6.5 times 2 on the calculator, 13. And there we go. I've now written it in that completed square form. And it did say where a, b are integers. So we do have integers. We have 2 lots of x minus 2 squared and then minus 13. Right, there we go. So we have our completed square form. I just need to now write down the coordinates of the turning point of that graph. Now the turning point is exactly the same as normal completed square form. So when I have, and I'll just rewrite this, 2 lots of x minus 2 squared minus 13. Our x coordinate is this number in the bracket, but with a flipped symbol. So it'd be plus 2. That's our x coordinate. And the y coordinate is just this number at the end. We don't change the symbol. It's just minus 13. And there we go. And that would be our coordinate for our turning point. So it's positive 2, negative 13. There we go. And that same method applies even if we don't have a coefficient of x squared that's greater than 1. Okay, on to our next question. So question 24, we have a vector proof. So it says here OMA, ONB and ABC are straight lines. Basically every line that we can see there is a straight line. M is the midpoint of O to A. Well, straight away, I'll label these as 1/2. B is the midpoint of A to C. Okay, so this is halfway as well. And then it tells us O to A is 6A, O to B is 6B, but O to N is K lots of B, where K is a scalar quantity. So we don't know how far along the line O to N is. But O to A is 6A, but these were in halves, so that would be 3A and 3A, paying attention to the direction of the arrow there, because we're moving from O to A. O to B is 6B, and we don't know how that splits, so I'll just label that 6B. And then, given that MNC is a straight line, find the value of K. So M to N is there, and then N to C takes us down to here. Now my diagram doesn't make it look like a straight line, to be fair. It's close enough, but it's not drawn to scale. But it tells us it's a straight line, so we're going to assume that it definitely is a straight line. So to figure this out, we need to have a think about some of the vectors in terms of how to get there. Now, if we're looking at this straight line, there are 3 vectors that we could be looking at. We could look at the entire straight line if we can figure out a way to get there, and we'll have a look at that in just a minute. And then we also need to have a look at one of either this little line here or this line here, and look at one of them separately. So once we've done that, we can compare the vectors and see if they match up and see if it is definitely a straight line. Now normally the full line can be found relatively easily, so we'll have a look at how we get from M to C. So to get from M to C, I need to first think about how to get from B to C, because we don't have that vector. All we know at the moment is that A to B and B to C are the same length, as B is the midpoint. So let's look at finding A to B. So to get from A to B, which is currently the line that we've not been given, to get from A to B, I would have to go up from A to O and then down from O to B. So to get from A to O, I would do minus, because I'm moving backwards, 6A, and then plus 6B. And that would get me from A to B. I'd go up to O and down to B, but I'd get there. So to get from A to C, it would be exactly the same as that, or from B to C. So to get from B to C, it's going to be exactly the same as A to B. It's exactly the same line, it's just B is in the middle. So B to C is also minus 6A plus 6B. And if you prefer, you can write that as 6B minus 6A. You can write them the other way around. But that's the order that I've moved in, so I'm just going to keep it like that. So now I can get from B to C, I can start having a think about how to get the full length of that line from M to C. So to get from M to C, and let's just draw this route on because it's quite an extensive one now, I'm going to go up to here, down to here, and then I'm going to do B to C, which we've already found. Of course I could move down as well. I don't have to go that way. I could go down here, across here, and then the full length. It really doesn't matter. We're going to get the same answer either way. It's just personal preference at this point, which one you prefer. But I'm going to stick with this one. Let's see what we get. So M to C, I'm first going to do the minus 3A to go up to O, then plus 6B as I move down to B, and then B to C is minus 6A plus 6B, which is just the line written above. So I just need to tidy this up. Minus 3A minus 6A is minus 9A, and then 6B plus 6B is 12B, so plus 12B. So that is how I get from M to C, and that's one of the lines in this question that we have to find. So typically at this point, it's also very good practice to now factorise that particular vector. So they both divide by 3, so I can have 3 on the outside, and then I would have minus 3A plus 4B. And there we go. Now I'm going to highlight that one because that is a very important vector that we've just found. Now, if we look at either of the two lines that we mentioned then, so M to N or N to C, those vectors, whichever one we find, have to share that particular bracket that we've got there. It has to share the multiple minus 3a plus 4b if it is on the same straight line. So can we find m to n? M to n we can start to have a look at. So if I look at the vector m to n, part of that we don't actually know because it says it's k lots of b. But let's write down what we do know. So to get from m to o, you can write this down as a big vector like this if you want. We'll go from m to o and then add to that o to n. That's the movement that we're doing. So m to o is minus 3a. Well, that's a good start because we wanted minus 3a, plus we don't know how much b because it says o to n is kb. So kb. Now if we look at the vector that we've just found and what we've just discussed, we've just said that the numbers in front of a and b need to match. Now currently we have minus 3a, which matches our a, so that's good, but the b we don't know, but it has to be, we've just said, has to be 4b. So k has to be 4. That's the only thing that's going to give us that minus 3a plus 4b. So here k has to equal 4, and actually that is the end of the question. We have found that value of k. Now you could have taken maybe a different approach as well. You could have looked at n to c and maybe thought about that being sort of a k lot of b. It would be a little bit more complicated because n to b is a sort of different number as well. Or actually we'd end up finding, because the full length of the line is 6b, if we'd have gone n to b and b to c, we might have been able to find that that gap from n to b was 2 lots of b. Because we know the top bit now is 4 lots of b, the bottom bit would have to be 2 lots of b. But you just want to be careful with that because we are looking at that o to n being the k. So if you did go n to b, you'd probably find the number 2 there and you wouldn't want to get confused between the two. So there we go. That was k is equal to 4 and that was our final answer. K equals 4. Kind of write that down here. There we go, just the answer is 4. And there we go. There is the end of that paper. So finishing off on a vector proof question, but remembering vector proofs, there are so many different types of questions that you could have. So I will link in the description the videos for the harder vectors where you have ratios involved and things like that, and just being able to make sure that you can pick up a couple of marks even on those hardest vector proof questions. And when it comes to those very, very difficult ones, typically I wouldn't say the questions are necessarily designed to get full marks on. It's just about what can you get any marks on, can you have a go, and if you have time left at the exam, could you sit there for 5 minutes just having a go and trying to figure out any particular missing lines or vectors to pick up an extra few marks. Obviously, if you really like vectors and vectors is one of your favourite topics, you probably want to practice those anyway, just to make sure that you are super confident on them, as they are, I would say, probably one of the hardest topics on the GCSE. But there we go. I will link that all in the description, along with any videos I've mentioned throughout this one. But otherwise, that's the end of this paper. And obviously, I wish you the best of luck going into your Paper 2 exam. I will have more videos ready for you, ready for Paper 3, which I'll link in the description as well. But otherwise, good luck in your exam, and I'll see you for the Paper 3 topical videos. Now, hopefully you've got your revision under control and you are making great progress towards Paper 1. But if you're struggling to know where to start and need to maximise your maths in minimum time, then you should sign up for my Rapid Revision Programme Upgrade, as you can use it to build your very own personalised revision plan. Which means all you need to do is complete my revision quiz and you'll know exactly which lessons or topics you need to work on to maximise your maths in minimum time. This is my paid programme, but you can sign up for a free trial on my website now. And if you feel like you need top tier support direction from me, then sign up for my live weekly interactive lessons, which include revision specific lessons focusing on the topics that I expect to appear in exam papers 1, 2 and 3.